and let's get started, right? Okay, so this is going to be the main act of this conference today. It's a Java conference, but you all came for the SQL tricks. I know this. So this is the 10 SQL tricks talk that you didn't think were possible. And I always say as well, 10 SQL tricks to convince you that SQL is awesome. Who am I? Oh, actually, I don't see the next slide, so I might be off by one slide from time to time. Why are you here? Because clickbait headlines really do work. Trick number 3, for instance, changed work forever. Trick number 8 makes doctors hate you. And trick number 9 is larger than life. So these kind of titles, they always attract audience, and I'm very happy to share these things with you. Me, myself, I'm the founder and CEO at Data Geekery. Simon already told you that this is the company behind Juke, and I'm also very deeply involved with everything Java and SQL related. And I believe that SQL is a device whose mystery is only exceeded by its power. And after this talk, you're certainly going to agree with me on this one. Why do we even talk about SQL? SQL is the only ever successful mainstream and general purpose fourth generation programming language. So we're going to see what that means later on, but it's really the most awesome one that does these kind of tricks and that does fourth generation programming. Why doesn't anyone else talk about SQL at any sort of conference, not just the VJUG, but wherever you go, no one talks about SQL? I don't know. Who uses SQL? Everyone does. So if I saw your hands, I would make you raise your hands right now, and you will all raise your hands and you will say, okay, I use SQL, and no one talks to me about SQL. People talk about fancy new concepts that no one uses or needs any yet, while everyone uses SQL and no one talks about it. What is SQL in the end? SQL is the original microservice. Few of you might have known this, but think about it. Just install a single store procedure in an Oracle Express Edition instance, deploy, and you're done. That's a microservice, right? So normally I try to be funny with this talk. I have no idea if you're laughing right now. Just assume that if something doesn't really make sense in the talk, it's probably going to be a joke, right? So I'm going to try this on the virtual jug style. Who in here or who among you thinks that this is SQL? And now again, you would see all your hands and everyone would say, I agree, this is SQL. So who would say that this here is SQL? Who would say that they're writing SQL like this with these annotations? And again, many of you will raise your hands because in the end, that's how many people write SQL in the Java ecosystem. Then we can go on and say who in here does SQL like this. We have all these join table and join column annotations, and maybe you're doing SQL this way. Probably. Is this the right way to do SQL? No, that's not the right way to do SQL. SQL is something entirely else. And I borrowed this slide from Marcus Winnen, who is a famous SQL consultant from Austria. Are you still using Windows 3.1? No. So why are you sticking with SQL 92? A lot of people that work in the Java ecosystem have no clue what's going on in the SQL world. And the SQL world has evolved a lot since the last time you've learned something about SQL. So SQL 92 is ordinary, select from where, join. But a lot of new things have happened. And today we're going to talk about what has happened since then. Okay, so this is also SQL. If you just let this sink in, and this is from a blog that usually does very nice posts every end of the year. So Happy New Year is the blog post title. And the guy actually does all these magic SQL statements that do magic tricks. If you mentally process this SQL statement right here, and you come to the conclusion that this is the result, you see this is possible with SQL. I've generated recursively a Mandelbrot set. In the SQL console, I have the output. This is a very nice example of recursive SQL, which we're going to see deeper later on. So SQL is actually Turing complete, right? Not that many of you might have known this, but SQL is Turing complete. And what does that mean? And when you're next time when you go to a party, you can impress your friends and talk about Turing completeness. This is what it means. It means that any program can be written in SQL. This is really true. So with SQL 99 and recursive SQL, you can actually implement any program in SQL. That means arbitrary complexity can be put into the database for calculation in a declarative way. So in a declarative way, this means it's a fourth generation programming language, as I told you before. This means you tell the machine what, not how. So you're not saying, machine, do this if this condition is true and then do that 5 times. No, you're saying, this is the kind of result I want. This is how it looks. These are the constraints on the result. And then the machine figures out the algorithm. So if you think about fourth generation programming languages, what do you think is more interesting for you? What is more modern? This thing? Oh, this is actually a fifth generation programming language. So do you think this is more modern, or do you prefer this approach? right? So the imperative programming paradigm is really something that everyone understands, but it's very low level, it's very primitive, and fourth generation programming languages are actually very modern, even if the syntax doesn't look like it. So this is also the reason why the company is called Oracle. The Oracle database is actually an Oracle. You ask it a question and somehow magically it gives you the answer, right? Okay, but what's the problem with SQL? Why don't people talk about SQL? Why do people feel that SQL is old technology? One of the biggest problems with SQL is this. Everything that you see here that is marked in green, everything that is green are keywords. So SQL is a very, very verbose language. So people often criticize syntax because it reminds them of this language here, right? So people think, okay, just because SQL is an old language, it's kind of the similar language like COBOL or Fortran or all these old things with capital letters and weird statements. So admittedly, the SQL syntax is awkward. It's kind of weird. It's kind of weird to write keywords, all of that many. And we're used to languages like Scala today and modern languages like Kotlin, where everything is very expressive. SQL doesn't look this way from a syntax perspective, but don't be blinded by syntax. It's just syntax. Another thing that people don't like about SQL is the fact that declarative thinking is hard, right? So you're used to saying machine do this and then do this and then do that, and that's very easy to do. And declarative thinking is very hard because you have to think about telling the machine what you want as a result. Not telling the machine what to do, but telling the machine what you want as a result. So this is the same thing when you ask your spouse something at home, your husband or your wife. You want to tell them what you really want. You have to think much harder to find out what you really want than tell them what they have to do, right? So this is why declarative thinking is hard. But there are a lot of things that are much easier with SQL than with any other language. So if you do reporting, complex reports, that's much more easy with SQL than with any other language like Java. If you write a report with Java, it's extremely hard. You have to write unit tests and everything. With SQL, no problem. Just declare the result and you get it. Bulk data processing is very easy with SQL. So if you have a lot of data and you express the algorithm with SQL, it's very easy to shift data around between tables or even between databases. It's very easy to do with SQL. Adhoc analytics, that's even the major winning point or selling point of SQL. So when you have a normalized schema and you analyze it and you have to figure out, okay, I have these tables and now I want to see what kind of data do I have, you can very easily write just a SQL statement, just writing a Java program that actually analyzes your data. You will be still writing that program 3 weeks from now, while with SQL, 10 minutes is easy, right? And by easy, I mean very hard, but you don't have a choice. So this is how SQL works. SQL is a tough language. It's a difficult language. It takes practice. And I have this quote from Winston Churchill. He was believed to have said SQL is the worst form of database querying except for all the other forms. But luckily, every one of you has this SQL muscle. So all of you are equipped with this muscle. You have this muscle, and the only thing that you have to remember from this talk is this is the SQL muscle, and it needs constant training and practice. SQL is a difficult language at first, but you have to practice it. And suddenly, with this muscle, as with every muscle that you train, it becomes easier and easier. Conversely, I also have found a picture of the Java muscle. So this is the Java muscle, you know, imperative programming, a lot of force. You tell the machine what to do, and the Java muscle has a Latin name. So the Latin name goes by this. This is the Latin name of the Java muscle. Okay? But enough of the blah blah. You came here for 10 SQL tricks. This was just the introduction, and the 10 SQL tricks come now. And these are the 10 SQL tricks that we're going to talk about today. And maybe I can't show you all the 10 SQL tricks because usually this talk takes 1 hour, so I only have 45 minutes. Excuse me if I have to skip through the last 2 ones. These are the 10 SQL tricks to convince you that SQL is awesome. At the end of this talk, you will all feel like this. Okay? Ready? No? No, it doesn't matter. We'll start with SQL trick number 1. Oh, by the way, while I was preparing this presentation, I noticed I did so many slides. There are roughly 5,700 slides, and I really don't have any time to do all of these slides in a very convenient manner, so I have to talk very quick. And while I did all of these slides, I thought, let's thank our patron saint, Eder for having invented programming, because without having invented programming, we programmers could write awesome SQL statements. We would have to do something like PowerPoint or something, right? So we're all glad we can do programming with awesome SQL instead. Okay, trick number 1. Everything is a table, right? So in SQL, everything is a table, just like in relational algebra, everything is a set. You have to always remember this. So most of you can spot the table, and when I ask you to spot the table, you think this is the table. The person thing here, that's the table. But also, there's another table in this statement, and that's this one. The whole statement is a table. So everything in SQL is a table. If you think about it this way, you can just move this select statement in a from clause like this, and then you have something like a derived table. That's what it's called. A derived table is a select statement in the from clause. So that's also a table. And you can take this further and put something like the values constructor in the from clause. This is supported in this with this syntax in SQL Server and Postgres, for instance. Values constructors help you create in-memory tables. So these are tables, and you can put them in the from clause and put a derived column list there, so you can rename the table and the column in one go. So that's an in-memory table. Everything in SQL is a table. If you think about SQL this way, you will find a lot of very, very nice features in the SQL language that actually operate all on tables. And you can join these things and select from these things and do many magic tricks. So when you see the values clause, you've already probably seen the values clause before. The values clause is actually the same thing as the values clause in the insert statement. When you use an insert statement, you're actually transferring a table to another table. You're not inserting one row by row. So that's probably the mindset you might have when you're using JPA or something else in Java. You're inserting individual rows, but actually that's not what you're doing. You're inserting a table that happens to have one row most of the time, but you can add more rows to the values clause and insert more rows at once into another table, right? So this is very important. Everything in SQL is a table. And if you don't have the values clause, you can just write select union all select, like in Oracle, for instance, which doesn't have values clauses. You can select data from the dual table and use the union operator to create multi-row tables in memory. And if you're using Postgres, which is one of the fanciest databases from a syntax perspective, then everything is really a table. So for instance, this function is a table. Substring is an ordinary function, but it returns a one-by-one table. You can put that into from clause and you can join it. This is really magical. So everything is a table. Please remember, everything is a table. Now you compare that with Java 8. Java 8 finally has something that is like SQL. The Java 8 API has the stream API, and if you think of tuples in SQL, they're the same thing as classes in Java. So a class has attributes, tuples in SQL have attributes as well. They're like tables, right? So a table is a stream of tuples. In Java, select is the map function on the stream. When you select something, you're actually transforming each individual tuple into a new tuple, and that's the same thing as using the map function. Distinct exists on both sides. Join is the same thing as flat map, conceptually at least. Where and having is the same thing as filter. Group by is the same thing as collect. And order by is the same thing as sorted, whereas union is the same thing as concat. So everything in SQL has something equivalent in Java 8 using the stream API. Or let's put it the other way around, because SQL is much more advanced, but at least you have the similar mindset. And if this is not enough for you, well, a little bit of advertising, we have a better streams API, which is called the Julambda library that we do as an open source library. Rabia Gransberger will talk about this in a later talk and compare it with other Java 8 APIs. So whenever streams are not enough for you because you want to have more SQL in Java, then you can use Julambda to do things like these. So you can have several aggregate functions very easily with the collect function here, and you can have a tuple as a result. So this will get all the persons and aggregate them into different values, right? So just try out Julambda and check out how you can write SQL in Java. Okay, that was trick number 1. Everything is a table. And trick number 2, I have to go quick. Trick number 2 is about common table expressions. That's the only way to declare variables in SQL. Often we want to use variables in SQL in other languages as well to decompose problems into smaller problems and solve the smaller problems first, and then build up the bigger problem on top of the smaller ones. So common table expressions are very easy to understand. We just reuse the with clause, and with the with clause, we have then the T1. I have a laser pointer here, so we have the T1 statement, the T1 table, and the T2 table. So both of these are tables, and we can use them as variables. And then here, I hope you don't see both pointers. I have 2 pointers. I hope you only have 1. But you can see the table in the other table, right? So this is very useful. You can declare variables and use them as tables. Everything is a table also when you use variables. So in the end, at the bottom, we have a select statement. And in the select statement, You can see here we're selecting from these variables, and that's the result we're getting. Now, the nice thing about common table expressions or these table variables is it can be recursive. So here I have Postgres syntax, so I need the recursive keyword. As you can see here, this statement is recursive, right? Yes, this is a lame PowerPoint joke. I stole it from Hadi Hariri from JetBrains. Sorry for the steal, but I found it quite apt for this presentation. Okay, with recursive, so we have a table that we declare, and the table is called T, right? So we declare the table T, and when we declare the table T, we select from T. As you can see right here, we select from T, while we declare from T, and the first row that we declare inside of T is just the seed row. It starts with just one row, and then we select that row again and add one to it. And then we stop the recursion with the limit 5 statement at the end. That's just how we generate values from 1 to 5. This works in pretty much every modern database. And Oracle and some other databases have a simpler syntax. We're using connect by. Connect by also starts a recursion, and the recursion level is defined by the level pseudo variable. So you can just add a predicate on the level variable to stop the recursion at the level 5. So that's the same thing. As we've seen before, this example here that I've shown you, which is Turing complete, shows we have a recursive SQL statement as well. So if you follow the top left laser pointer here, we have the Q table. We define the Q table, and we select from it recursively. The Mandelbrot set is a very nice example of recursive calculations. So you can try this out at home using Postgres database, and you can study recursion in SQL. So there are a couple of applications for recursion apart from academic examples. You can, for instance, iterate in the database from 1 to 10. Sometimes you need these data. You don't have them in a table, so you can generate them in memory. Or you can generate all dates in July 2016. Let's imagine you have to write a report, and the report goes over all the dates in July 2016, but your database table doesn't have all the dates, so what you have to do is you have to generate them in memory. Or you can generate graphs. And we're going to see an example of generating a graph in the database afterwards. Of course, you shouldn't use these features too often. If you have a lot of graph problems, use a graph database. But sometimes you only have 1 or 2 graph problems, and you want to solve them with SQL because you don't want to have a separate database just for one problem, right? So that's trick number 2, recursive SQL data generation. Awesome. Trick number 3 is running total calculations. Trick number 3. So how do we do a running total in SQL? And what is a running total? If you don't know what a running total is, ask your project manager. He knows, and he will give you a crash course about the awesome Microsoft Excel. Next year at the VJUG, I'm going to give a talk about Microsoft Excel, which is even more awesome than SQL. But today we're going to talk about SQL. Okay, so in Microsoft Excel, a running total looks like this. You can just add a formula. So for instance, here we have the balance and the bank account. And we have amounts for each transaction. So these are the individual transactions. And on each transaction, we want to calculate the balance. So the balance is a formula that depends on the previous balance and the previous amount, right? And then in Microsoft Excel, you can just use the crosshair cursor and drag and drop this formula through your spreadsheet, and automatically you get the right balance in each cell. That's a running total because you run through your Microsoft Excel spreadsheet and you run the calculation through it, right? So that's a running total. How do we do that with SQL? We're going to do that with window functions. And we're going to have to learn about window functions first. What are they? And I promise you, there was SQL before window functions, and there was SQL after window functions. And there is you before this talk, and there is you after this talk. After listening to this talk, you will do everything with window functions. And you will stop coding Java and write all your logic with SQL window functions, right? Okay. So what are window functions? Window functions, and this is my definition, are aggregations or rankings on a subset of rows relative to the current row being transformed by select. This is a lot, and it's going to be a bit complicated if you've never heard about it, but don't be afraid. It's not that complicated in the end. You have to think about a SQL statement like this. When you have the from clause and the where clause and all of these clauses, and those clauses produce rows, right? So they produce rows, and finally with select, you have, like in the streams API, you have the map function. So you generate tuples and then you transform these tuples. Usually, while you run select, you can only access the individual tuple. So you can only access the data in the same row. Window functions change all of this. So with window functions, you can span a window And this is how you define it. You have these three clauses in the over clause. So the over clause specifies how big is the window. And you can then, within the window, look ahead and behind. So when you run a select clause, you can use a window function and you can access the next row or the previous row or all the rows. That's pretty powerful, right? So window functions are aggregations or rankings on a subset of rows relative to the current row. So let's go through this by example. Here we have a movie database. So these are films. And we're going to use a window function to calculate the row number of the films. So here we have films with title and film lengths. First off, we specify a partition for the window function. So the partition is kind of like the group by clause. We say partition by length. This means the window is only as big as all the rows that have the same length as the current row. So whenever we calculate, for instance, a window function on the row number 3, so we're on this row here, chi homeward, and we calculate the window function on this chi homeward row here, then we're going to see the partition. The partition is the length, and the length is 46. So the window is only all the other rows that are also of length 46. So that's the window. We have access to only the partition. The next partition would be all the rows of length 47. So when we calculate the window function, we don't get access to the other partitions. We only have our own partition. By default, the partition is all the rows. If you leave away this clause, you get all the rows. And if you have a partition by clause, you only get the rows of the same partition. Now, the partition can be ordered. So within each individual partition, we can specify an order by clause. So you see the first partition is ordered by title and the second one as well. They're ordered individually, right? So we order this by title, and then we can say, okay, we have this optional rows clause. When we specify it, we can say, I want to look beyond so many rows in advance and so many rows behind, right? So rows between so many rows behind and advanced. For instance, in this example, I'm going to look 2 rows behind and 2 rows ahead. In the end, I have the window function itself. The window function assigns, in this example, a row number. So within the partition, as you can see, each individual partition has their own row numbers. So the first partition had row numbers here from 1 to 5. And the second partition has, and again, row numbers from 1, 2, 3, 4, 5, 6, 7. The row number is assigned for each partition and given the ordering, right? So that's already it. These are window functions. So window functions are aggregations or rankings. So in this case, we had a ranking, but every aggregate function is also a window function. So window functions are aggregations or rankings on a subset of rows relative to the current row being transformed by select. Okay? Okay, let's do this and let's apply this to the running total example. So here we have again the bank account transactions. When we have bank account transactions, we can calculate the balance with window functions. That's what we're going to do right now. So for instance, if you have the balance on row number 4, the balance on row number 4 is equal to the top balance. So here we're on row number 4 is equal to the top balance minus the amounts, the sum of all the amounts that are on top of it, right? So all the amounts on top of it are summed and then subtracted. This is done very easily here with this. So once you get used to the syntax, you get this sum here, and then you specify with the over clause the window, and the window is specified using the account ID. So we don't want to have the neighbor's bank account transactions, obviously. Then we order all the transactions by value date and ID, and then we specify the window of all the rows that are on top of the current row, right? That's already it. So we have tool set for all the remaining tricks. Remember, from this talk, there are 2 advanced SQL features that you should know. These are recursive common table expressions and window functions. Now that we have the tool set, you are probably ready or not for the rest of the tricks, right? And don't worry, if this is how you feel right now, if you've never heard of this, remember you have a SQL muscle and it just needs practice. All you have to do is practice, right? Okay. So, trick number 4, finding the largest series with no gaps. If you're working on Stack Overflow, and like me, I'm a fanatic. I never spend time with my kid and my wife. So I visit the site every day for 100 consecutive days to get the fanatic badge. How do I get that? It's because in a series of 100 days, there's absolutely no gap where I didn't log in. By the way, I also have these incredible amount of reputation on Stack Overflow. Just be sure to have all of these things. It's one of the best things to get hired, and you absolutely have to have them. Okay, Stack Overflow. These are my login times. Okay, login times. And first step, I want to remove the time information. I only want to have the date information. And now, when we have the date information, I immediately see there's a gap right there, right? So between this row here and that one, we have a gap. So the longest series is 14th, 15th, or 16th of March. And how do we find this? Okay, the first step is very easy. We just cast the login time as a date, and then we distinct it. We get the distinct dates, and we have all the distinct login dates for my user. Okay, this is easy. Now, step number 2 for this trick is we calculate the row number. And the row number, we've seen before how it works. We just want to have 1, 2, 3, 4 on each login date. Why we want to do this, I'm going to show in the end, but this is what we want to do. And we're going to select the login date and the row number over the window ordered by login date, right? So this is very easy. We have row numbers for our login dates. Exactly. Now, what happens if we subtract the row number from the login date? Actually, most SQL databases have this very interesting feature. When you subtract an integer from a date, you get another date, and the integer was the number of days. That's very useful, right? So we do this, and we get a new column, and we call it group. What's interesting about this group column is we get a gap. We get a gap again, because 14 minus 1 is 13, 15 minus 2 is also 13, 16 minus 3 is also 13, but 18 minus 4 is 14. So when we had a gap before, we now have a gap again in the group, except that the group values are the same for the series. Right? Consecutive row number and the gap. Does this ring a bell? I'll leave it up to you to prove this, but the row number function, it never has any gaps. It produces unique values without gaps, whereas our data also has unique values, but it has gaps. This trick has a name. I forgot the name, but it works every time. So you just do this trick, and then you group by the group value. So we don't care about the resulting date. We just group by it right here, and then we do some minimum, maximum, and off by 1 error handling, and we get the length of the series. So the longest series is the one from March 14 to March 16, and this is the whole SQL query that we wrote to do this. It takes a little bit of time to actually have the idea, but it's very easy to understand. When you read this SQL statement and you start using window functions and you start understanding them, and with common table expressions as well, you can very, very easily understand what's going on in this SQL statement, and you can easily solve these kind of problems with only declarative features, right? Too easy. Okay. Next trick, trick number 5, finding the length of a series. Okay, so we're going to do a lot of series here. And what is the series? We want to find lengths. So you see these lengths here, and you see immediately the first series is of length 2 because there are 2 positive amounts. Here we have 3 negative amounts. 2 positive amounts, 1 negative amount, 1 positive amount. That's a very nice business case for our managers. We don't care about why they want to do it this way. We just implement the SQL query, right? Okay, so how do we do this at first? First off, we get rid of the rest that we don't care about. We only want to have the sign. We don't care about the amount itself. So we use the sign function to get 1 or minus 1 instead of the actual amount. And again, the row number was so useful before. We're just going to calculate it again. So this is how we calculate this result. Sign of the amount is the sign value, and the row number over the window ordered by ID descendingly is the row number. Okay, that's very easy. Now, what we want to do next is we want to calculate low and high. What are these low and high values? So in the first series, you see the low value is the row number at the lower end of the series, and the high number is the row number at the higher end of the series. You see it even better here. So the low value here, the 3 is the row number at the lower end of the series, whereas the 5 here is the higher, the row number at the higher end of the series, and in the middle of the series we just don't have anything. We just have these nulls. Okay, 6 and 7, 8 and 8, 9 and 9. Why do I want to do this? We'll see in the end, but this is the next step I want to do. And I'm going to calculate this once more with window functions. This time I'm going to use lead and lag. Lead and lag are the easiest to understand window functions, and they're very useful because I'm just simply going to access the next row or the previous row. So again, we're going to use values here to calculate, to generate an in-memory table of values 1, 2, 3, 4. You can see the values again in V, right? So V is the values. And then we have the lag function. With the lag function here, we can access the previous row. So you see on the second row, lag evaluates the expression V for the previous row. So we go to the previous row, we see what is V on the previous row, and then we put that in the current row. right? And lead is the opposite. Lead calculates the expression v from the next row. So when we calculate lead here, we go to the next row and we evaluate this v here in the next row. But we put the result in the current row. So lead and lag are the easiest to understand window functions, and they show you the power of window functions. We can access the next or the previous row. And by default, the offset is 1. But you can also optionally put a second parameter where you can say the offset. So you can say, I want to go 2 rows ahead, right? So you want to have the value of v 2 rows ahead. You write lead v and comma 2. So the next step is just to compare. What we're comparing here is the lag. So we compare the previous value of sine. We compare that with the current value of sine, and if that's not the same thing, then we put row number in the low column. If the next value of sine is not equal to the current value of sine, then we put the row number as the high value, and that's already it. So as you're going to go back, as you can see here, you see the previous value of sine here is different from the current value of sine, so that's a condition to put the row number in the low value. And if the next value of sine, that's here, is different from the current value of sine, then we put the row number in the high value, right? I really do hope you see my laser pointers at the correct spot. I'm sorry otherwise. Okay, so then we do a little bit of null handling, and that's boring, and we finally got low and high at the right spot. But we don't want to do that. We actually want to put low and high in each and individual row. So how do we do this? We just put them on each individual row, 8, 9, 9, etc. That's with this trick. I'm not going to explain the details here. I'm just going to tell you, okay, we have the first value and the last value window functions, which are similar to lead and lag. So first value just gets from a window the first value, and the last value gets from a window the last value. Okay, and we're using this ignore nulls clause here, the ignore nulls clause here in the middle. That's specific to these databases that you see at the bottom. It just says we ignore all the nulls in the window. It's just a nice additional trick. A little bit of null handling that's boring. So we're going to see in this example here, in this example, we're going to see, okay, this is, we want to put a 3 here. So we're just going to go up in the window from this row, and we're going to ignore all the nulls that are on top of it, and then we're going to take the last value of the window on top of it. So all the rows on top of row number 5 are in the window on top of it, and we're going to ignore all the nulls and then take the last value. Whereas in the high column, in order to put the 5 on every individual row, we're going to ignore all the nulls and then take the window below it and then take the first value of the window, right? So I'll let you read all these details in the end. It's a bit fast and it's a bit tricky when you see this the first time, but this is very easy to actually fill out all the values in each individual row. So in the end, we just do some mingling with off by 1 errors, and we have the length column. 1 plus high minus low is the length, and we have calculated the length of each individual series, right? So that's one way to solve this. There are probably other ways that are easier to understand than this one here, but this is a very nice educational example to show you how window functions work. Okay? Still okay? No? Yes? Trick number 6, the subset sum problem with SQL. What is the subset sum problem? We have an explanation right here. You can click on it after this talk. There's a boring explanation. I'm also going to explain it to you with an example. So for each of these are individual totals. We want to have these as a result. Okay, for each of these 3 results, we want to find the closest sum that is built from these items here. Okay? So from these items, we take a sum and we calculate the sum and to get as close as possible to each individual totals of the ones on the left. So the result, if you calculate this in your head, is this one, right? So for 25,150, the best possible sum is 25,133. Okay, and this is how we calculate it. That's the subset sum problem. Subset sum problem has a very naive possible exponential algorithm to solve it, and we're going to use that one because it's naive and easy to implement. There's also a faster solution with a polynomial complexity. It's approximative, so it's not exact, but it's way too complicated to implement with SQL today. It's already good enough to use this one. Okay, so this is the simple explanation of what we're going to do. We're going to write a common table expression that we call sums. And we calculate all the possible 2 to the power of n sums at first, and then we find the best total, the best sum for each individual total, right? So that's the easy trick. You ready? You feel like this? I don't care. Let's go on and do the trick. Okay, I'm going to explain the algorithm step by step with this easy explanation. Okay? So these are the possible sums. On the left side, we have all the items. So when we take the first item, on the right side, we have something like a conceptual stack. Don't take it very detailed, it's just an example. So we have the first item, that's already a possible sum. 7,120 is a sum. And we can combine this item with all the remaining sums. My notation is sums of ID 2 to 10, right? So we can take, for instance, the next item and put that in the sum. And then we can combine this additional possible sum with all the remaining sums. And for instance, we can skip 3 items and take item number 1 and 5, and we can combine this item with all the remaining sums. So that's how we calculate all the possible sums, and you immediately see why it's exponential, because for each individual item, we can decide, is it in the set or not, right? Okay. Are you ready? So this is how we do the possible 2 to the power of n sums. We do it recursively, and in the first iteration of the recursion, I'm using Oracle syntax. This is why I don't have to put the recursive keyword. So in the first iteration, I just do all the items. Each individual item is a possible sum. So I just take all the items, and that's one of the sums. Okay? So the first column of the sums table is the sum column. The second column is the ID column, and the third column is the calculation column. The ID column is just the latest ID that I've considered for the sum. Now the recursion is not that complicated. What I'm doing is, for each individual sum that I've already calculated, I join again all the items. But I only join those items that are bigger than the largest item that I've already considered. As in the algorithm that I've explained before, I'm just going to add each individual sum and going to combine that with the remaining sums, right? And then inside of the iteration, the item is just added to the previous sum. So the sum is equal to the item plus the previous sum. The largest ID is just always the largest ID. And the final calculation column is just a string concatenation of each item to the previous string concatenation, right? So this is how I recursively construct all the formulas to calculate these sums. And now the second step is very easy, actually. I have all the sums, I have all the possible sums, and for each of these sums, I want to get as close as possible to one of these 5 totals. I'm just going to do this cross join here. So the cross join means for each total, I combine each total with each sum. This is kind of like a deck of cards. So each rank is combined with each suit. That's a cross join. And once I've done that, I'm just going to do a group by. As you can see at the bottom, I'm just going to group by all the totals and then take the minimum value of the absolute difference. This will give me the best difference. That's already good enough. So this is the best difference to achieve when you want to get as close as possible to 25,150 is 17. And we actually don't want to have the best difference, but the best sum. Here I'm using some Oracle trick. You can study this in detail afterwards, but the idea is clear, right? So I group by all the sums. I group by the totals. In each group, I have all the sums, and I find the best sum for each total. Okay? That's the whole query to solve this problem with SQL. It's not that hard. It's not that hard. It's a lot of keywords. You have to get used to it. You have to practice it, but it's very easy. I've never declared anything in the algorithm. I never did anything of the algorithm. I just declared everything. Now, Simon, can you hear me? How's my time? Simon?
So yeah, I'm here. Sorry. So you have got 7 minutes left, but we can go. We can go a little bit further over if we don't take questions as well.
I have to speed up. Okay, thank you very much, Simon.
All right.
Capping and running total. So I'm going to skip through tricks 8 and 9, but I'm going to tell you trick number 7 here is capping and running total. So the running total must not be less than 0, right? So this is one way to calculate running total. So before we've seen running total with window functions, this one is a bit different because we want to say, okay, when we go below 0, as you can see here, when you see this row here, when we go below 0, we're a very generous bank and we give an unlimited credit to our customers, and they never go below 0, right? So when they cap their bank account, when they crack it, we still just give them the money and put 0 in their bank account. Okay, so you could do this with the greatest function. So we just always take the greatest value of 0 and the actual sum, the actual balance. How do we do this? With Microsoft Excel, it's very easy. We just put the formula greatest into each cell and we have solved the problem. Now, Microsoft Excel is the original reactive programming application. And this means we can do reactive SQL as well. Because we can do SQL, we can do spreadsheets in the SQL database, right? I'm going to show you afterwards how this works. How do we do it? Window functions? It's probably not possible. I've tried it, it's very, very hard with window functions. Recursive SQL, yes, it's possible with recursive SQL, but now we've learned recursive SQL and it's too boring. Are we going to use obscure vendor-specific SQL? Yes, exactly. Someone else will maintain it, right? So we're going to use some obscure vendor-specific SQL, and we're going to feel like this because our coworkers have to maintain it the day after we've solved it. And we're going to use Oracle's model clause for this. Oracle has a very, very nice model clause, which means we can write spreadsheets, SQL statements. Awesome. Model clause. You can put just model after any table, and then you have these three clauses here, the dimension, measures, and rules clauses, which are essentially the same thing as Microsoft Excel. So with the dimensions, you can have the spreadsheet dimensions, like in Microsoft Excel. The measures clause says what you put into each individual cell. So in Oracle, you can put several values inside a tuple, and the rules is a list of all the rules that you have put into each individual cell. In Microsoft, you have to put the rule inside of the cell. Here, you can put a list of rules, okay? So let's start. We're going to prepare the data. That's easy. We'll just put 0 at the total, in the initial total, and then we put the model clause. We dimension our spreadsheet with a row number, because row number is so useful for these kind of things. Okay, so we have a dimension calculated by the row number, and then we put into each individual cell, we put the results we want to have, the date, the amount, and the total, and then these are the rules. It's very simple. So the total of any row number, any here means the row number, the dimension is the greatest value of 0, and the total of the current value, so CV means current value, of the row number minus 1. So this is essentially just the row number on top, and we're accessing the total of the row number on top of the current row. Exactly? You got this? No? But think of Microsoft Excel. It's just very easy. Just have the same formulas, and you can use all sorts of recursive formulas in these kind of rule statement, and it's very easy to do that. It's not very easy, I lied, but there's a big and very nice, I'm going to skip through this. It's a very nice Oracle model white paper. Just Google for this, and you can solve a lot of very interesting problems, spreadsheet-like, in your database if you're using Oracle. Now, I'm really sorry, I have to speed up. Normally, this talk takes 1 hour. You can skim through the slides. They're online. This one, trick number 8, would be time series pattern recognition, where you can actually pattern match a series to find an event. I'm just going to skip through this, just give you the hint in the end. The solution, this would be the solution. You use a regular expression in the middle of the SQL query, also if you're using Oracle. So you have a regular expression where you can pattern match your events. And this is very, really sophisticated stuff when you do something like fraud detection. You want to have a time series, and you have several events, one after the other, and you want to detect these kind of patterns with regular expressions. I'm sorry I have to skip through this. The talk is online as well if you want to hear the solution step by step. And this is my joke about Oracle, because Oracle, I mean, you pay already so much, but you have these very, very nice advanced SQL features. It's one of the most advanced databases for these kind of reports, right? So there's also a very nice Oracle Match Recognize white paper, which I recommend reading. Just Google for it, and you will find the whole details, right? Okay, now that you're experts, this would be almost too embarrassingly simple, so I'm also skipping through this. This is about pivoting and unpivoting. Okay, so pivoting means when you have this kind of table and you want to pivot, this is how you pivot something. So you have new columns for each value, and then you aggregate inside of the column, and the unpivoting operation is the inverse. So in the trick in the end, I'm just going to tell you there's a clause in SQL Server and Oracle for pivoting and or unpivoting as well, and that's how you do it. Very simple. If you ever want to pivot or unpivot, this is how you do it, right? Pivoting and unpivoting. Easy. So the final trick is XML and JSON in the database. This is what it came here for. So XML and JSON in the database is something like of a big hype. We had XML 10 years ago. Today we have JSON. So I have to tell you a word of truth first before we delve into this problem. JSON is just XML with less features and less syntax. Okay, so this is the truth. You can argue, doesn't matter. It's the truth. And everyone knows that XML is awesome, and soon I'm going to do an excellent XSLT talk because it's so awesome. And now if we apply XML is awesome to this sentence here, then we could just see JSON is less awesome because less features and less syntax, right? Okay, so that means we're going to skip the topic of JSON in the database, just look at XML in the database. And yes, this is my next talk about XSLT because it's so awesome, more awesome than SQL. Okay. So here we have an XML document. We want to parse this, and we have a list of films per actor. It's comma separated. This is how we do XML, right, with comma separated list. And we want to have a table of actors and films and their relationship, right? This is the result we want to have from this XML document. How do we do it in SQL? Easy, just with recursive SQL, 3 steps. First off, we parse the XML statement, and that's the hardest step, right? Just parse the XML statement here, Postgres syntax, and then we have an XML data type in our database. And then second step, we just do a little bit of XPath and unnesting and etc. And we generate the ID value with the row number. We all like and love XPath. And the third step is, I'm going deliberately fast with this because it's so easy. We're just doing some recursive SQL. We pattern match with regular expression. We find the first comma in the comma separated list, and that's our first film. And then we recursively search for the next film and the next film until we find out that we have no longer any commas left, and that's the last film. So we do this recursively with regular expressions. What's better than SQL? It's regular expressions inside of SQL plus XML, right? So this is the final comment about regular expressions. I think you all agree. So this is the 10 SQL tricks. I'm sorry you've seen only 8 today to convince you that SQL is awesome. Please do visit trick number 8 and 9 as well, because they're even more awesome than the first ones. And I'm sure you're convinced now. Now, what does awesome even mean? I looked it up because I'm not a native English speaker. Awesome means a feeling of fear and reverence. It also means a feeling of amazement, right? You're all amazed. But what is amaze? A maze, I've looked it up. I tried to understand what is a maze. A maze is a labyrinth, a puzzle consisting of complicated network of paths and passages. And I think I like the trick, the explanation number 3 at most. It's confusion of thought, perplexity, uncertainty, that state of bewilderment. I'm pretty sure that's also how you all feel. And how do you write bewilderment? You write it with the word wild. And I looked this up. No, I didn't. It's just a joke. But why do I talk about SQL? SQL is the only ever successful mainstream and general purpose 4th generation programming language, and it is awesome. Everything that I've showed you today is declarative. I didn't write one single algorithm. The database will figure it out for me, and that's really, really great. Can I do SQL in Java? Yes, I can. We have Juke. Juke is an excellent library that does all these tricks in Java. It helps the Java compiler understand SQL. So whenever you have a SQL statement and you write it with Juke, the Java compiler will type check it for you. You change the column name, it will no longer compile. This is how you can finally write SQL in Java after years of being deprived of SQL in Java, right? Okay. What's the key takeaway? What did you learn today? Can you do it in the database? Yes, I've proven it's Turing complete. You can do everything in the database. Can you do it in the database, dear audience? I'm sorry about that. Can you do it in the database? Yes, you can as well. Now you know all the tricks. And if you don't know all the tricks in detail, we offer a 2-day SQL training, which is a link. There's a link here. If you're in Zurich, we also do it internationally. So with the 2-day SQL training, I'm guarantee you that you can do it in the database as well. Can you do it in your database? Yes, you can. All of what I've shown you today, except for some fancy Oracle tricks, are available in all commercial databases and in Postgres. It's all the SQL standard features, right? We know functions, recursive common table expression is a SQL standard, and you can do it in your database, except maybe if you're using MySQL, which is way behind all of this, okay? Should you use it in the database? No, I'm just kidding. In the day, because we've seen someone else will maintain it. So easy to write, so easy to forget. Okay, do listicles attract attention? This also worked. Will this talk ever end? Yes, it will right now. Sorry for the 5 minutes overtime, and thank you very much for your attention. Don't forget to book our training and learn more about SQL. Thank you very much.
Thank you very, very much, Lukas. That was a true masterclass in not just not just SQL, but also how to give a presentation. Very, very entertaining, and I enjoyed that a lot. I think this is maybe the 2nd or 3rd time I've seen this session, and I enjoy it just as much every single time. Very, very funny. We have got time for a couple of questions, actually. Mimic47 in IRC asks, in trick 7, couldn't we just use triggers?
Oh, at trick 7, couldn't we just use triggers? Okay, let's see. Do you see it? Do you see my slide?
No, you've stopped showing your screen, actually.
I've stopped sharing the screen. That doesn't help. So let's try this again. Whole screen. Yeah, now we can see it. Trick number 7. With triggers. That's an interesting question. I've never thought about this. You can do everything with triggers, of course, because triggers uses a lower level programming language like PL/SQL or something like that. But why would you use triggers for capping a running total? You probably do that when you insert the data, right? So you can always, you can always pre-calculate data. So all the tricks I've shown you today calculate data on the fly, right? So when you do SQL statements, you calculate everything on the fly in memory, but you can obviously calculate stuff before you insert that into the database. You can have a total column and not calculate that on the fly. So obviously, yes, you can.
And one comment in from Ilan Pillimer. Triggers are Turing complete too, apparently. So there we go.
Awesome. Sorry, yeah, they're Turing complete. Absolutely.
Awesome. So thank you very, very much, Lukas. I think that's all we've got time for. Really, really fun session. Really, really good timing. And welcome again to the Virtual Jug. It's always a pleasure to have you.
Thank you for having me.
Thank you very much. Right. So where are we now? Okay.